A moving locomotive carries thousands of tons of forward momentum. When approaching a curve, physics dictates it wants to continue in a straight line. Forcing it into a circular path generates a distinct outward pull, centrifugal force. That force is equal to the vehicle's mass times its velocity squared, divided by the radius of the turn. Double the weight, you double the outward force. Double the speed, you quadruple it. And the tighter the turn radius, the more aggressive that lateral pull becomes. Adding to this physical stress is a mechanical constraint unique to railway rolling stock. Train wheels are locked together on a solid, rigid axle. The left wheel and the right wheel spin at the exact same rate. They cannot rotate independently. Place that rigid axle on a curve, and you run into a geometric wall. The arc of the track's outer rail is physically longer than the arc of the inner rail. Since the rigid wheels must turn together, covering those different distances would normally force one wheel to violently skid or slip along the steel, chewing up the track and creating extreme instability. Yet a train has no steering mechanism. It negotiates these bends entirely through the physical interplay between the shape of the wheels and the geometry of the track. Resolving this rigid axle paradox is how civil engineers safely redirect thousands of tons of kinetic energy without tearing the infrastructure apart. The first mechanism solving this problem is built into the train itself. Railway wheels are not perfect cylinders. They are tapered, built with a specific coning ratio that typically slopes inward at 1 in 20. On a straight track, this rigid axle sits perfectly centered. The rails make contact with identical points on both wheels. In this position, the active rolling radii match exactly, covering the same distance with every rotation. Entering a curve, centrifugal force pushes the rigid axle outward. This lateral shift forces the outer wheel onto the thicker, larger diameter portion of its cone. Simultaneously, the inner wheel settles onto the thinner, smaller diameter section of its cone. At the contact patch, the disparity creates a distinct difference in the rolling radius. With a larger active radius, the outer wheel travels physically further on every rotation, perfectly matching the outer rail's longer path without slipping. This is passive self-steering. The rigid axle automatically adjusts its geometry based entirely on the turn's physics, requiring no mechanical linkages. By relying on a simple taper, the train navigates standard curves by transferring the burden of steering to the shifting radii. But wheel coning has strict limits. If lateral forces overwhelm the taper, the wheel shifts too far, causing the flange to strike the outer rail. This metal-on-metal contact creates severe wear and the risk of derailment. To prevent flange strike at speed, civil engineers modify the track itself, using a technique called superelevation, commonly referred to as Cant. Cant banks the track structure, tilting the train inward. This introduces a gravitational vector down the slope, directly opposing the outward centrifugal force. When balanced, the axle shifts back to the center, safely pulling the flange away from the rail. Designing for Cant requires splitting the track into separate structural segments. In the center is the circular curve. Here, the radius remains uniform, and the track is banked at a constant, maximum angle. This angle is calibrated for an equilibrium speed, where the inward tilt and outward force perfectly cancel out. A train cannot safely jump onto a fully banked curve. Engineers insert a transition curve, bridging the straightaway and the turn. Here, the radius tightens and the outer rail rises, smoothly ramping up the cant and applying lateral forces progressively. Negotiating a high-speed bend safely requires engineering the approach to the curve just as strictly as the curve itself. Using abstract center point radii to plan these curves is useless to the crews responsible for building them out in the field. Instead, engineers use a practical metric to quantify track sharpness, the degree of curve. The degree is defined by the angle subtended at the center point by a standard 30.5-meter chord along the outer rail. This provides a conversion formula. The degree equals exactly 1750 divided by the radius in meters. This formula establishes rigid safety baselines for entire rail networks. For example, the absolute minimum permissible radius is strictly 175 meters, which converts exactly to a 10-degree curve. Even with this conversion, maintaining alignment presents a severe logistical problem. A track inspector cannot hike hundreds of meters into a forest to locate the curve's center just to verify the radius. The solution is measuring the track using the Versine or Mid-Chord offset method. By pulling a 20-meter wire across the track's inner arc, inspectors create a chord. Measuring the perpendicular gap halfway along that line to the railhead gives the Versine. These measurements overlap every 10 meters, continuously monitoring the steel's smoothness. If the track shifts by even a few millimeters under heavy loads, checking these Versines allows crews to detect and correct the structural disturbance directly from the trackbed. It reduces abstract geometry into localized physical mathematics that rail crews can execute on the ground. Blueprint geometry only works if it can be translated into physical, measurable chord data that ensures the steel holds its precise shape. When you watch a massive heavy-haul train negotiate a sweeping landscape curve, you are seeing all of these elements functioning as a single system. At the approach, the transition curve smoothly ramps up the cant, tilting the carriages inward to cancel out the train's massive lateral momentum. Through the apex, the track maintains uniform curvature, a geometry verified by strict Versine measurements along the chord line. Beneath the carriages, the rigid wheel sets quietly slide outward, allowing the wider profile of the coned wheels to cover the longer path of the outer rail, keeping the flanges clear. A curve is a highly active physical environment, engineered entirely to counteract the mechanical realities of the rolling stock. By combining the passive geometry of the axles with the rigorous mathematics of track layout, engineers manipulate physics to keep thousands of tons safely in motion.